For a stationary time series, the expected value is constant over time, and the autocovariance depends only on the lag, that is, the difference between the time values of the observations. We can say that the expected value of x sub n is equal to mu, some constant that doesn't change over time, and this holds true for all n values. That is, there's an identical copy of this equation for every value of n. We can also write this as a vector equation by using a Greek letter subscript and the convention we introduced in the previous lesson, according to which the Greek letter subscript means that we're referring to the entire vector rather than an individual value. But we cannot say that the expected value of x sub alpha is equal to mu, because this particular equation really doesn't make sense. On the left-hand side, we have a vector, the expected value of x sub alpha being a vector itself. Therefore, we would have a vector of expected values. But on the right-hand side, we have mu, which is a constant, which is not a vector. It's a scalar. It's just a single number. Well, we can make this all mathematically rigorous correct by introducing a remarkably useful quantity, the unit vector. I'll write it as a great big boldface number 1 with a alpha subscript. It's a vector, and it's a vector for which all the individual components are equal to 1. So we can say that boldface 1 sub n is equal to 1. And here I've used a Latin index to indicate that this equation refers to the individual values. So we actually have a separate copy of this equation for each possible index value n. And with that in hand, we can express the constancy of the vector of expected values of the time series by saying that the expected value of x sub alpha is equal to mu times the unit vector sub alpha. And therefore, we have an equation which is an equality between two vectors. A vector of expected values on the left, and a constant mu times a vector which is the unit vector on the right. Now, this distinction may not seem very important or useful at this time, but later on, a considerably while later on, its value, I hope, becomes clear. What I'd really like to talk about in this particular installment is something extraordinarily important. It's called the variance-covariance matrix. We can express the time translation invariance of the covariances between different time series values by saying that the covariance between x sub j and x sub k is some function that depends only on the difference between their index values. In particular, the absolute value of the difference between their index values. And that expresses the fact that covariance depends only on the time difference, that is to say, the lag between the values. Even if the time series is not evenly spaced, we could say that the covariance between different values is some function of the time difference. Whether a time series is stationary or not, we can arrange the covariances of the values into a variance-covariance matrix. And all I've done here is take the covariance values between two different values and made them a particular entry of a matrix, which I called by the uppercase Latin letter V. And note that the diagonal elements, those for which j equals k, are the variances of the individual values. The off-diagonal elements, those for which j is not equal to k, are the covariances between different values. And that's where we get the name variance-covariance matrix. Some authors use the uppercase Greek letter gamma to represent the variance-covariance matrix, but I prefer the symbol V because I often use the uppercase Greek letter gamma for other uses. Now, the previous expression is a whole set of equations. There's one for each pair of TS values x sub j and x sub k. I can write it as a single matrix equation by just using Greek letter subscripts to indicate matrix. And here I have a single equation rather than something that represents a whole set of equations that gets repeated again and again. The variance-covariance matrix is fundamental in time series analysis. Its importance can hardly be overstated. Because multiplication is commutative, the variance-covariance matrix is a symmetric matrix. That is to say, the covariance between items j and k is the same as the covariance between items k and j. We can write this as a genuine matrix equation by a very similar notation, but it's not actually an equation about individual values. The quantity v sub beta alpha is not some particular entry of the matrix. It's a matrix itself, which is the transpose of the matrix v sub alpha beta. When the time series is evenly sampled and stationary, we have that the variance-covariance matrix is some function of the absolute value of the difference between index values. So its value depends only on the difference. This means that the values are the same, they are unchanged, when you're looking at the variance-covariance matrix and you move up and to the left or down and to the right around the matrix. Because when you do that, the difference between the index values doesn't change. Any matrix which has this property, that the values are the same when you move up and to the left or down and to the right, is called a Toeplitz matrix. Therefore, for an evenly sampled time series, the property of being stationary is equivalent to the two requirements that the mean is time independent and the variance-covariance matrix is a symmetric Toeplitz matrix.